Let's talk about complex numbers. So we're on our quest to understand eigenvalues better, and the next big problem we want to tackle is the problem of finding eigenvalues. However, to actually solve this problem, we need to understand a little bit more about some classical mathematical topics. These topics involve complex numbers. So what is a complex number? By definition, a complex number is an expression of the following form. We're looking at number z that can be expressed as a number b times I plus another number a. So what are the ingredients into this expression? This number I is the most important part of this expression when defining complex numbers. This number I is the famous so-called imaginary unit, and this is a number I whose square is equal to -1. This number a, which is not being multiplied by I, is called the real part of this complex number. And sometimes to denote the real part, people write fancy r of the complex number. And the stipulation here is that this must be a real number. This number b that is being multiplied by I is called the imaginary part of the complex number. And sometimes people write fancy I of the complex number to refer to the imaginary part. And this is also supposed to be a real number. Now, we denote the collection of real numbers by fancy R. The collection of complex numbers is denoted by fancy C, like this. So, for example, the number 3i minus 2 is a perfectly good complex number. The real part of this complex number is equal to -2. That's the part of this number that is not being multiplied by I. The imaginary part of this complex number, 3i minus 2, is the part being multiplied by I, which is equal to 3. Okay, so one thing to point out is that every real number can be viewed as a complex number where the imaginary part is equal to 0, but not every complex number can be viewed as a real number. So if we wanted a visual representation of this statement, the idea is that all of the real numbers, which are denoted by fancy r as a collection, so for example, some of those numbers are 17, 0, -11, pi, e, etc. Each one of those numbers can be viewed as a complex number where what we're doing is we're taking the real part, so maybe for the number 17, the real part is 17, and then we have imaginary part equal to 0. So every real number is a complex number. However, not every complex number is a real number. For example, the numbers down here, 3i minus 2, -7i plus 1, -16i, etc. These are all perfectly good complex numbers, but none of these numbers is a real number because their imaginary parts are non-zero. The imaginary part of 3i minus 2 is 3, the imaginary part of -7i plus 1 is -7, and the imaginary part of -16i is -16. So the punchline here is that every real number is itself a complex number, but not every complex number is a real number. Okay, so how do we do arithmetic with complex numbers? Well, to add two complex numbers, the formula is pretty straightforward. If we want to add a complex number b1 times I plus a1 to another complex number b2i plus a2, what we do is we compare the imaginary parts of these complex numbers, in this case b1 and b2, we add them together, and then we multiply by I. So the imaginary part of this addition of the two numbers is equal to the sum of the two individual imaginary parts. Then we look at the real parts, a1 and a2, and we add those together, and that sum becomes the real part of this sum of two complex numbers. So addition is straightforward. The product of two complex numbers has a more complicated formula, but the formula is derived from the ordinary product of the addition of two numbers. So if we take b1 times I plus a1 and multiply by b2 times I plus a2, well, to multiply these numbers together, what we do is we multiply everything out term by term, and we use the property that I squared is -1, and we end up with an expression where the new imaginary part is a1 b2 plus a2 b1, and then the new real part after multiplying is a1 a2 minus b1 b2. So this is a good exercise proving this formula to convince yourself that you understand how to do some of the basic manipulations of complex numbers. There's also an important operation on complex numbers, and this is the notion of conjugation. The conjugate of a complex number is obtained notationally by just writing a bar or a line over the top of the whole complex number. And this is a simple operation. All we do to conjugate b times I plus a is we negate the number b. So to conjugate is to negate the complex part or the imaginary part of the complex number. The absolute value makes sense in the world of complex numbers. What we do to take the absolute value of a complex number is we sum the squares of the real part and the imaginary part, and then we take a square root. So here are just a few examples illustrating each of those formulas. To add 4i minus 3 to negative I plus 1, what we do is we take 4 minus 1, because those are the two imaginary parts of these complex numbers, and that becomes the new imaginary part of our addition. So 4 minus 1 will be the imaginary part of this sum. The real part will be negative 3 plus 1, which of course is equal to negative 2. So 4i minus 3 plus negative I plus 1 is 3i minus 2. If we apply our formula for multiplication from the previous slide to 4i minus 3 multiplied by negative I plus 1, we end up with the new complex number 7i plus 1. Again, this is a good exercise to go through on your own to acquaint yourself with this arithmetic. Conjugation, for example. So here we're taking 4i minus 3 and we are conjugating. Again, to conjugate, all we do is take the imaginary part and negate. So the conjugate of 4i minus 3 is negative 4i minus 3. And what about absolute values? To take the absolute value of 4i minus 3, we take the real and imaginary parts of this number, square them, add them, and then take a square root. So here we're looking at negative 3 squared, because negative 3 is the real part of this number. Then we're adding 4 squared, because 4 is the imaginary part. So negative 3 squared is 9, 4 squared is 16. When we add those together, we get 25. And then after taking a square root, we get 5. So the absolute value of 4i minus 3 is equal to 5. Okay, so let's take a closer look at this operation of conjugation. So again, conjugation is a simple operation, but it ends up playing an important role in the arithmetic of complex numbers. So for one, conjugation is additive. What this means is that if we conjugate an addition, z1 plus z2, that's the same thing as conjugating individually and then adding the two results up. It's also multiplicative. What this means is that if we multiply two complex numbers, z1 and z2, and then conjugate, that's always the same thing as individually conjugating the two complex numbers and then multiplying them together. And it's also an involution. If we conjugate a complex number twice, we get back the original number. Well, why does this work? Well, to conjugate once, we negate the imaginary part, and then to conjugate twice, we negate again, so we get back to the original imaginary part. We also have a nice formula that relates the absolute value of a complex number to its conjugate, and the formula says that the absolute value of a complex number is equal to the square root of that number multiplied by its own conjugate. So to take the absolute value, we multiply a number by its conjugate, and then we take a square root. And if we think about how conjugation works, the way conjugation works is we negate the imaginary part of the complex number. And this ultimately gives us an algebraic way to test whether or not a given complex number is actually a real number. To say that a number z is a real number is the exact same thing as saying that its conjugate is equal to itself. Because if we negate a number and that end up not changing the number, that means that number was 0. So if we negate the imaginary part of a number and end up not changing the number, that means that the imaginary part was 0, which means that the number itself was a real number. And these formulas allow us to define division in the world of complex numbers. The reciprocal of a complex number of the form b times I plus a is written just the same way that we write the reciprocal of an ordinary number. We're taking 1 divided by z here, if z is the label for our complex number. And the formula for reciprocals says we form a fraction where the numerator is the conjugate of the complex number and the denominator is the square of the absolute value. If we follow the formulas for conjugation in absolute values, we realize that what we're doing is we're constructing a new complex number when we take the reciprocal of a number, and the complex part, or the imaginary part of this reciprocal, is negative the original imaginary part divided by the sum of the squares of the real part and the imaginary part. And then the real part of this reciprocal is the original real part divided by the sum of the squares of the real part and the imaginary part. So this is what allows us to do division with complex numbers. And this formula is derived from the formula for absolute values. The absolute value of a number is the square root of the product of the number with the conjugate. So the absolute value squared is the number multiplied by its conjugate. And the formula we just derived is obtained by dividing both sides of absolute value squared equals the number times its conjugate by the conjugate. So for example, what is the reciprocal of the complex number 5i minus 2? Well, according to our formula, we should form a new complex number where the imaginary part is the fraction where the numerator is the negation of the original imaginary part, and the denominator is the sum of the squares of the real and imaginary parts. Well, for the number 5i minus 2, the original imaginary part is 5, so the numerator of this new imaginary part should be negative 5. The denominator of this imaginary part should be the sum of the squares of the real part and the imaginary part. So now we're looking at negative 2 squared, which is 4, plus 5 squared, which is 25, which gives us a denominator of 29. The real part of this reciprocal should be the original real part divided by the sum of the squares of the real part and imaginary part of the original number. So now the original real part of 5i minus 2 is negative 2. So now we get negative 2 in the numerator. Then we're dividing by the sum of the squares of the real part and the imaginary part, which we just found to be 29. So the reciprocal of 5i minus 2 is negative 5 over 29i minus 2 over 29. So complex numbers play an important role in the theory of polynomials, and polynomials will be the fundamental tool we use to find the eigenvalues of a matrix. So let's do what I hope is maybe a mini review of some basic statements about polynomials. So a polynomial in a variable t is an expression f of t of the following form. We take a scalar c sub n and multiply by the variable t raised to the raised to the n. Then we take another scalar c sub n minus 1 and multiply by t raised to the n minus 1. And we keep adding terms that look like this until we get to a scalar c sub 1 multiplied by t to the 1, and then we add a constant c sub 0. The degree of a polynomial is always the largest exponent of our polynomial. So if we assume in our expression here that this number c sub n is not 0, that would tell us that the degree of our polynomial here is n. One of the special types of polynomials we will study is a monic polynomial. A polynomial is called monic if the coefficient of its top degree term is equal to 1. So let's look at some examples of polynomials. Here we have the polynomial f of t equals t squared minus 2 times t plus 3. This is an example of what's called a quadratic polynomial, meaning that the degree of this polynomial is 2. And we can see that here, the term with the biggest exponent is t squared, and here the biggest exponent is 2. Here's another polynomial. This one is negative t cubed plus t squared minus t. This is an example of a cubic polynomial. Cubic means that the degree is equal to 3. And we can see the degree here is equal to 3 because the largest exponent in any of these terms is in the first term here where we have t cubed. Our next example is f of t equals 20 times t to the fourth plus t cubed minus t. This is an example of a quartic polynomial, which means that the degree of this polynomial is 4. And here's an example of what's called a quintic polynomial. This polynomial is t to the fifth plus 2 times t to the fourth plus 2t cubed minus t squared plus t minus 10. We say this polynomial is quintic, and what we mean by that is that the degree is equal to 5. The largest exponent in any one of these terms is in the first term here, where we have t raised to the fifth. Let's determine which of these 4 examples is a monic polynomial. In our first example, the term that has the largest exponent is the first term here, and the coefficient in front of this first term is equal to 1. If we were labeling the coefficients, here we would label the first coefficient here as c sub 2 equals 1. We would label this next coefficient as c sub 1, which would be negative 2. And we would label this last coefficient as c sub 0 equals 3. Monic means that the coefficient of the term with the largest exponent is equal to 1. So this first example is a monic polynomial. This next example is the cubic. And if we look at the term that involving t to the 3, we see that the coefficient is negative 1. So this is an example of a non-monic polynomial. Our second example here is not monic because the coefficient of the term with the biggest power is equal to negative 1, which means that the top coefficient is not 1, which means this is not a monic polynomial. Our quartic example is not monic either. The coefficient of t to the fourth in this quartic is equal to 20, which is certainly not equal to 1. So this third example is also not a monic polynomial. In our last example, we're studying a quintic polynomial. That means that the degree is 5. If we look at the t to the fifth term, we see that the coefficient is equal to 1 here, which means this is a monic polynomial. So as soon as we write down an example of a polynomial, it's relatively simple to find the degree. We just look at all of the terms and find which one has the largest exponent and then record that exponent. To determine whether or not that polynomial is monic, we look at the coefficient of that term and verify whether or not it's equal to 1. Okay, so when people study polynomials, one of the things that they search for are the roots of that polynomial. What is a root of a polynomial? A root of a polynomial, f of t, is a scalar r that satisfies the equation f of r equals 0. So if we are given a polynomial and we want to verify whether or not a given number is a root, all we do is we replace t with that number. So we plug in t equals that number, and we check whether or not the output of that replacement equals 0. So here we have an example of a cubic polynomial, which happens to also be monic. And what I've done here is I've replaced t with a few different values. Here in this first equation, I set t equal to 1 and evaluated the resulting expression, and I got the number 0. Then I replaced t with the number 2, evaluated the resulting expression, and I got the number 0. Then I replaced t with the number 3, evaluated the expression, and I got the number -4. These three calculations tell me information about the numbers 1, 2, and 3 in relation to the polynomial. When I plugged in t equals 1, I got 0, and when I plugged in t equals 2, I got 0. What this tells me is that r equals 1 and r equals 2 are roots of the polynomial, but when I plugged in t equals 3, I got -4, which is not equal to 0, so that tells me that r equals 3 is not a root of this polynomial. Okay, so roots of polynomials are one of the first things that mathematicians studied historically. So we know a lot about the structure of roots of polynomials. One thing we know about the roots of a polynomial where the coefficients are real is that the roots always occur in conjugate pairs if we have roots that are complex but not real. So this next theorem says the following. Let's say that our polynomial is an expression where all of the coefficients of the powers of t are real numbers. So what this means is that none of the coefficients have imaginary parts that are non-zero. It turns out that if little r is a root of this polynomial, then so is its conjugate. So if we have a root of a polynomial with real coefficients, we can conjugate that root, and the conjugate is also a root of the polynomial. This, the proof of this theorem is relatively straightforward, so let's look at it step by step. Let's say that we plug in the conjugate r bar into the polynomial. So what we're doing is we're replacing all of the t's here with r bar, or the conjugate of r. Well, what we're looking at is c sub n times r bar to the n, plus c sub n minus 1 times r bar to the n minus 1, and then we keep doing this until we get to c sub 1 times r bar plus c sub 0. So we're replacing all of the t's in our expression for the polynomial with the conjugate of r, where here we know that r is a root of the original polynomial. Well, what is this expression? This turns out to be the same thing as conjugating every single term here. And the reason that we can conjugate each one of the coefficients of this polynomial is that the assumption is that each one of those coefficients is a real number. And remember, if real numbers do not change when we take conjugates. And one of the things we said about conjugation is that when we conjugate a product, we end up, or when we take a product of two conjugates, that's the same thing as the conjugate of a product. So this term c sub n bar times r n bar is really the same thing as c sub n times r to the n bar. And this next term, c sub n minus 1 bar times r to the n minus 1 bar, is the same thing as c sub n minus 1 times r to the n minus 1 bar, and so on. And another thing we said about conjugation is that it's additive, meaning since we're adding a bunch of conjugates here, that's the same thing as just conjugating the entire expression. And now if we look at everything under this line, we're looking at c sub n times r to the n plus c sub n minus 1 times r to the n minus 1, and we keep going until we get to c sub 1 times r plus c sub 0. Well, this is the same thing as taking the conjugate of what we would have obtained if we just replaced t with r in the expression for the polynomial. And the assumption in this theorem is that little r was a root, which means we're really looking at the conjugate of 0, which is itself equal to 0. So this concludes the proof, saying that if our polynomial has real coefficients and we know one of the roots is little r, we know that another one of the roots is the conjugate of little r. Okay, so we now have enough language to state one of the most famous mathematical theorems, and that is the Fundamental Theorem of Algebra. The Fundamental Theorem of Algebra says the following. Let's say that we're studying a monic polynomial, and what that means, again, is that the coefficient of the term with the largest exponent is equal to 1. If our polynomial is monic, then the Fundamental Theorem of Algebra says that our polynomial factors as the product of a bunch of terms, where each term is of the form t minus one of the roots raised to some power. So here our polynomial factors as t minus r1, where r1 is a root, raised to the m1, multiplied by t minus r sub 2, where r sub 2 is another root, raised to the power m sub 2, and we keep going until we get to the last root, r sub k, and the last term is t minus r sub k, raised to the power m sub k. So every polynomial factors like this, where r1 through rk are the distinct roots, and note that these might be complex numbers that aren't real, and if we sum each one of the powers in this factorization together, we always get the degree of the polynomial. And this factorization is unique up to a reordering. So if we manage to factor like this, we always get the same thing, except maybe two different people factor like this, and they just reorder the terms. In this factorization, there is important language. The power of t minus ri to the mi, so this number m sub I or m sub j here, if we're looking at the root r sub j, is called the multiplicity of the number as a root of the polynomial. So let's look at a particular application of the fundamental theorem of algebra. Here, I've defined a polynomial in terms of its factorization. So here I have a polynomial f of t, and this is defined as t minus 3i plus 2 raised to the 3, multiplied by t plus 3i plus 2 raised to the 3, plus t plus 7, multiplied by t plus 7, multiplied by t minus 9 to the 4th. So each one of the factors in this factorization is of the form t minus a root raised to a power. So with this factorization, I can actually list off all of the roots of this polynomial. In the factorization, we have 1, 2, 3, 4 terms, which means this polynomial has 4 different roots. If we look at the first term here, we're looking at t minus 3i plus 2. If I factor out a negative here, I realize that I'm really subtracting off the number 3i minus 2 from t here. So the first root of this polynomial is 3i minus 2, and its multiplicity is equal to 3 because the power that we're raising this term to is 3. In the next term here, this term is t plus 3i plus 2 cubed. This is the same thing as t minus the quantity negative 3i minus 2 cubed. So the second root of this polynomial is negative 3i minus 2, and its multiplicity is also equal to 3 because the power in this term, or the exponent in this term, is equal to 3. The next term is t plus 7. T plus 7 is the same thing as t minus negative 7. So the next root is negative 7. And its multiplicity is equal to 1 because the exponent here is 1. And finally, the last term is t minus 9 to the 4th, which tells us that 9 is our last root, and its multiplicity is equal to 4. So by factoring like this, we're able to list off each of the 4 roots of this polynomial, and by looking at each one of these exponents, we can record the multiplicities of each of these roots. Another thing we can do with this information is we can infer the degree of this polynomial by summing up all of the multiplicities of all of the roots. So the degree of this polynomial should be equal to 3 plus 3 plus 1 plus 4, which equals 11. So this is a polynomial of degree 11. It happens to have 4 roots, 3i minus 2, negative 3i minus 2, negative 7, and 9. And the multiplicities of those roots are 3, 3, 1, and 4. One thing to pay attention to here is that this polynomial has 2 complex roots that are not real, and these 2 roots are related by conjugation for this example. 3i minus 2 is the conjugate of negative 3i minus 2. Okay, so the last thing we'd like to address is how do we find roots of polynomials? So if we simply start with a given polynomial, where do we get the roots from? And this turns out to be a very difficult problem. So this is a very old problem in mathematics, and it's really been the inspiration for the development of whole new fields of math. So the answer here is that it's actually normally hard to find roots of polynomials. There are, however, instances where finding roots is straightforward. And probably the most famous result in this direction is the quadratic formula. So what does the quadratic formula say? Well, the quadratic formula is a direct formula for the roots of a quadratic polynomial. So this can be stated as a factorization theorem. If our polynomial is of the form a constant a times t squared plus a constant b times t plus a constant c, we can always factor this polynomial as the leading coefficient a multiplied by the product of t minus each one of its 2 roots. And the 2 roots here are given by negative b, where b is the coefficient of t, plus or minus the square root of b squared minus 4ac, all divided by 2a. So for example, here we have the polynomial f of t equals negative 2 times t squared plus 8 times t minus 10. We can calculate the 2 roots of this quadratic polynomial by using the quadratic formula. The coefficient of t is 8, so in both of the roots, our numerator starts with negative 8. Then we look at plus and minus the quantity, the square root of b squared, which is 8 squared, which is 64, minus 4 times negative 2 times negative 10, which is minus 80, all divided by 2 times the leading coefficient, which is negative 2, which gives us negative 4 in the denominator. When we simplify these expressions for the 2 roots, we end up with negative I plus 2 and I plus 2. The 2 in both of these expressions is obtained by taking negative 8 and dividing by negative 4. And the plus or minus I is obtained by taking the square root of 64 minus 80, which is the square root of negative 16, which gives us 4i. And then minus 4i over negative 4 is negative I. And then when we take plus that radical over negative 4, we get plus I. And so this ends up giving us our factorization from the previous theorem. Our polynomial was negative 2 times t squared plus 8 times t minus 10. Our previous theorem says this quadratic factors as the leading coefficient negative 2 multiplied by the product of t minus each one of the 2 roots. Another thing to notice about this example is the 2 roots we found, negative I plus 2 and I plus 2, are related by conjugation, which is expected because this is an example of a polynomial where each one of the coefficients is a real number, which means that the roots of the polynomial occur in conjugate pairs. So we have a quadratic polynomial with real coefficients whose roots happen to be complex numbers that are not real, and the 2 roots occur in conjugate pairs here. There actually are formulas for some higher degree polynomials, but they're much more complicated. So it turns out that in addition to the quadratic formula, there is a cubic formula, and there's also a quartic formula. So if our polynomial has degree 3, there is a formula for figuring out the roots, and if the polynomial is of degree 4, there's a formula for figuring out the roots. These are two theorems that I've never bothered to learn because the formulas are quite complicated. But there is an interesting result of Abel from 1824, which says that there is no quintic formula. So Abel was a young mathematician who in 1824 managed to prove that there is no formula for the roots of a degree 5 polynomial in terms of the coefficients of that polynomial. So in essence, what he's proving here, or what he proved, is that the problem of finding roots of polynomials is a very difficult one. Okay, so now I'd like to say something about how the roots of a polynomial relate to the coefficients of a polynomial. So let's look at a small example where the degree of our polynomial is 2. Let's say that we're studying a monic polynomial of the form t squared plus c1 times t plus c sub 0. And let's look and see what the fundamental theorem of algebra says about this particular polynomial. What the fundamental theorem of algebra says is that this quadratic polynomial factors as the product of t minus the first root with t minus the second root. And if we expand this product, we get the expression t squared minus r1 plus r2 times t, that's the sum of the roots multiplied by t, plus r1 times r2, which is the product of the two roots. Well, we can look at this equality and match coefficients. The first thing to look at is on the right-hand side, the coefficient of t is negative quantity r1 plus r2. Well, that should match the coefficient of t in the original formula for the polynomial. So what this is telling us is that the sum of the two roots of this quadratic polynomial equals the negation of the coefficient of t in this polynomial. We also get another relationship by looking at the constant coefficient here. When we multiply out the product of t minus each one of its roots, the constant coefficient is plus r1 times r2, and that term should match with the constant coefficient of the original polynomial, which is c sub 0. So this gives us another equality, which says that the product of the two roots of this polynomial is equal to the constant coefficient of this polynomial. So what we have here for this quadratic polynomial is a relationship between certain amalgamations of the two roots with the original coefficients of the polynomial. The sum of the two roots is the negation of the coefficient of t to the 1, and the product of the two roots is equal to the constant coefficient of the polynomial. Our two equations that we just saw are symptomatic of a more general theorem, which is called Vieta's formulas. So what Vieta's formulas say is that the fundamental theorem of algebra can be expanded to give us relationships between the roots of a polynomial and the coefficients in the polynomial. So let's say that we're studying a degree n monic polynomial, and we manage to factor that polynomial according to the fundamental theorem of algebra. It turns out that the coefficient of t to the n minus 1, so this is the term with the second largest exponent of t, so the coefficient there is c sub n minus 1. It turns out that the negation of that coefficient is always equal to the multiplicity of the first root multiplied by the first root plus the multiplicity of the second root multiplied by the second root, and we keep going until we get to the multiplicity of the last root multiplied by the last root. So the negation of the t to the n minus 1 term is the sum of all of the roots where each root is multiplied by its multiplicity. There's also a formula relating the constant coefficient in the polynomial to the roots. And what this formula says is that if we take the constant coefficient and multiply by -1 to the degree of the polynomial, that is always equal to the product of all of the roots, where each root is raised to the power of the multiplicity. So let's see this as an example here. So here we have, again, our example of our polynomial factored according to the fundamental theorem of algebra. This factorization is telling us that our polynomial has 4 roots. The multiplicities of those roots are 2, 2, 1, and 4. Well, one thing we can immediately infer is the degree of this polynomial. The degree is obtained by summing the multiplicities of the roots. So the degree should be 2 plus 2 plus 1 plus 4, which is equal to 9. And Vieta's formulas in this case tell us what the coefficient of t to the 8 would be should we multiply out all of these terms in the fundamental theorem of algebra. It says that the coefficient c sub 8 negated should be equal to the sum of the roots where each root is multiplied by its multiplicity. The first root here is 2i minus 1, and we multiply 2i minus 1 by 2. The second root is negative 2i minus 1, and its multiplicity is 2. The third root is negative 7, and its multiplicity is 1. And the fourth root is 2, and its multiplicity is equal to 4. So we take each of the multiplicities and multiply by their roots. We sum everything up, and in this case we get negative 3. What that's telling us is that the negation of the coefficient of t to the 8 is equal to negative 3, which tells us that c sub 8 here has to equal 3. The second Vieta formula tells us how the constant coefficient relates to the roots. The constant coefficient is related by the formula -1 to the degree, which in this case is 9, multiplied by the constant coefficient, is the product of all of the roots, where each root is raised to its multiplicity. So here we're looking at 2i minus 1 squared, multiplied by negative 2i minus 1 squared, multiplied by negative 7 to the 1, multiplied by 2 to the 4th. And when we multiply this out, we end up obtaining negative 2800. And since negative 1 to the 9th is negative 1, this is telling us that the constant coefficient here is equal to 2800. So the Vieta formulas tell us how to take a factorization of our polynomial and relate that factorization to the constant coefficient and to the coefficient of the term t raised to the second to the largest power, or t to the n minus 1.